Hello everyone, welcome back. In this in this lecture, we will discuss about some numerical problems on the solar cells. Let's start. Here is the problem. You can see a solar panel measures 80 centimeter by 80 centimeter. This is the dimension of your solar cell. In direct sunlight, the panel delivers 3.2 amperes at 15 volts. That means uh, this is the solar cell that is giving you a 3.2 amperes of current at 15 volts. If the intensity of the sunlight striking the panel is 1000 watt per meter square, what is the efficiency of the solar panel in converting solar energy into electrical energy, right? So what is this they're asking is, we have a we have a panel. For example, let's consider we have a panel which is 80 centimeters width and 50 centimeters 80 centimeters long and 50 centimeters width, and there is a sunlight is falling. The sunlight is intensity is 1000 watt per meter square, and it is giving you a current of 3.2 amperes and 15 volts current. Now the question is, when 1000 watts per meter square is falling on the solar cell and it is giving you 3.2 amperes and 15 volts current and voltage, what would be the conversion of this sunlight into this current and voltage? How much is the conversion of this solar light into electricity? That is the efficiency, right? So normally we define efficiency, we define efficiency, right? Efficiency means eta. Efficiency means eta is equal to power output. This is the electrical power by this is the input power. Input power. This is the light power. If you wanted to have a percentage, then you can multiply with 100. This is the formula, right? Efficiency of the solar cell is output power by input power into 100 percentage. This is the output power from the solar cell. You get output power is electrical and input power is light, right? So now let us see what is the output power and what is the input power. Now you take the ratio between them and you can multiply with 100%. That gives you efficiency. Now let's start. So the panel area what we got is 80 centimeters long and 50 centimeters width. Now this is in centimeter, but you remember your incoming light is 1000 watt per meter square. So this is in meter square. So your units should be converted into meters. So that's the reason why we converted into 0.8 meters, 0.5 meters. So the total area is length into width. So 0.8 into 0.5 gives you 0.4 meter square, 0.4 meter square area, right? This is the area of your solar panel. .4 meter square. This is the area because we need this one. Although we got a light intensity 1000 watt per meter square, but we don't have a full 1 meter square. We only have a 0.4 meter square. So we need to find out how much is the light intensity falling on only on this area, not a complete meter square. This is for the whole meter square, but we don't have a meter square. We only have a 0.4 of the meter square. So we need to convert this 1000 watts to how much is the wattage that is falling on this area, right? So solar panel, now the solar power incident on the panel is, this is the 1000 watt per meter square, but we need to find out the power, the power incident on the solar panel in the area this much only, 0.4 meter square. So Pin into area is equal to 1000 plus into 1000 into 0.4, which gives you 400 watt. See, this is actually, if you wanted to see watt per meter square, this is a meter square, right? Meter square, meter gets cancels, then this is 400 watts. This is the the power which is actually falling on your solar panel, though 1000 watts are falling, if you keep 1 meter square, but we have only 0.4 meter square, so the total power falling on your solar cell is only 400 watts out of 1000 watts, right? So this is the input power, light power, which is falling on the solar cell. Now, for this solar cell, because of this 400 watts, how much is the current it is generating? Through 3.2 amperes and 15 volts. This is the current and voltage it is generating, right? Now we need to find out output power generated by the solar cell, right? So let's see the electrical power output, right? This will be normally, this is the current that it is producing the, right? We have a solar panel, and in this one 400 watts of power is falling on this solar panel. For this one it is producing 3.2 amperes and 15 watts. Now the current and voltage gives you power, we know, right? So the electrical power will be P is equal to IV, which is equal to 3.2 into 15, which gives you 48 watts, right? So when I give 400 watts of light, it is giving me a current electric power of 48 watts only, right? I'm giving 400 watts of input light power, but I'm getting only 48 watts of output power, right? So now the efficiency is simply P output power by P input power, right? Simply you take 48 by 400, that gives you efficiency, right? So now efficiency is output power by input power, right? This is actually, you can consider this whole thing is input power per unit area, right? This is a per unit area, so area both will cancel, P out by P in, right? You can simply write P out by P in into 100 percentage if you wanted to have in percentages, right? So now let us substitute 48 watts. 48 watts is the output power, this is the electrical power, right? And this is the total wattage that is falling per meter square, but we have only area of 0.4 meter square. So now you calculate 48 by 400, which gives you 0.12. Now this 0.12 will be multiplied by 100, which gives you 12 percentage, right? If you don't want to tell in terms of percentage, then answer would be 0.12 only. But if you want to tell in terms of percentage, then the 12 percentage of power conversion efficiency that your solar cell has, right? So we have a solar cell. Now, though 1000 watts are falling on this solar cell per meter square, but actual falling on the solar cell is 400 watts falling, but it is giving me only 48 watts of current. The ratio between these two gives me a 12 percentage efficiency. This is how we can calculate the efficiency of the solar cell. Thank you.